For millennia, humanity has dreamt of structures that defy limits, reaching the sky, burrowing through mountains, or traversing oceans. In the modern era, these dreams have materialized into megaprojects of unprecedented scale and complexity. This documentary delves into some of the world's most extreme contemporary engineering feats, examining the formidable structural challenges that engineers faced, and revealing the ingenious solutions that allowed them to build what once seemed impossible. We will probe the evidence, analyze the designs, and uncover the stories of projects that truly rewrote engineering history. What defines a megaproject? According to various engineering and economic sources, these are vast, complex undertakings, typically costing over $1 billion, impacting millions of people, and requiring years, sometimes decades, to complete. They push the boundaries of technology, materials science, and human coordination. The projects we examine aren't just big, they represent a fundamental challenge to perceived limitations, from the physics of wind loads on supertall structures to the geological unpredictability deep within the Earth's crust, and even the vacuum of space. Our journey begins in Dubai, with a structure that redefines verticality, the Burj Khalifa. Completed in 2010, this skyscraper, designed by Skidmore, Owings and Merrill, SOM, stands as the tallest building on Earth, soaring to an astonishing 828 meters. Its very conception challenged conventional wisdom on how high a building could stand. Sources from the Council on Tall Buildings and Urban Habitat confirm its record-breaking status. However, achieving this height was not merely a matter of scale, it presented an array of unprecedented structural and logistical hurdles. For a structure reaching such extreme altitudes, wind became the primary antagonist. As tall buildings ascend, wind speeds increase dramatically, creating complex forces that can cause sway, vibrations, and structural fatigue. Engineers at SOM, according to their project documentation, faced the challenge of designing a building that could withstand not just steady gusts, but also the unpredictable vortex shedding that can cause dangerous oscillations. Traditional rectangular designs would have been highly susceptible to these dynamic wind loads. To combat these immense wind forces, the engineers implemented a revolutionary buttressed core design, a Y-shaped plan that serves multiple critical functions. Adrian Smith, the lead architect, described it as a three-lobed plan that effectively confuses the wind. This geometric design continually changes the building's shape as the wind wraps around it, disrupting the formation of powerful vortexes and significantly reducing the overall wind loading and potential for motion sickness-inducing sway. It's a testament to biomimicry and aerodynamic principles applied at a monumental scale. Another critical challenge was the sheer logistics of construction, specifically getting concrete to the dizzying heights of the upper floors. Concrete is the fundamental building block of modern skyscrapers, but pumping it over 600 meters vertically was unprecedented. Industry standards and existing pump technologies simply weren't designed for such an extreme vertical lift. Sources from Samsung C&T, the primary contractor, highlighted that conventional methods would have made reaching the top levels practically impossible and economically unfeasible. The solution involved a combination of material science and specialized pumping technology. Engineers developed a unique, high-strength, self-compacting concrete mix, designed to be pumped efficiently without segregation, even under immense pressure. This specialized mix was coupled with custom-designed, high-pressure pumps. According to engineering journals like Concrete International, these pumps achieved world-record single-stage lifts, delivering concrete at rates and heights previously unimaginable. This innovation ensured the structural integrity of the upper levels and kept the project on schedule. From the vertical challenge of Dubai, we dive deep beneath the Swiss Alps to explore the Gotthard Base Tunnel. At 57 kilometers, it is the world's longest and deepest railway tunnel, a monumental feat completed in 2016. Its purpose was to create a flatter, faster route through the Central Alps for both passenger and freight trains. Alptransit Gotthard AG, the project owner, emphasized that this wasn't just about length, but about battling the extreme geology and conditions found up to 2,500 meters beneath the mountain's surface. Drilling through the heart of the Alps meant confronting infernal conditions. Engineers had to contend with geothermal temperatures reaching up to 50 degrees Celsius deep within the rock. This extreme heat, combined with immense rock pressure from the 2,500-meter overburden, created an incredibly dangerous and challenging environment for workers and machinery alike. Reports from the Swiss Federal Office of Transport detailed the constant battle against heat stress and the threat of rock bursts caused by the colossal forces. To overcome the heat and pressure, bespoke tunnel boring machines, TBMs, nicknamed Gabi and Sisai, were engineered. These mechanical behemoths, weighing thousands of tons and over 400 meters long, were equipped with advanced cooling systems to maintain operable temperatures. They bored through hard rock while simultaneously installing prefabricated concrete segments. Furthermore, sophisticated ventilation and chilled water systems were deployed throughout the tunnels to ensure worker safety and equipment functionality, as documented by Herrenknecht AG, the TBM manufacturer. The geology of the Alps is notoriously complex and varied, presenting another monumental obstacle. Engineers encountered everything from solid, crystalline rock to unstable fault zones containing crushed, watery material. This geological unpredictability meant that drilling speeds could vary wildly, and sudden shifts could trap machinery or cause collapses. Detailed geological surveys, while extensive, could not fully predict every pocket of weak or water-bearing rock, creating an environment of constant structural uncertainty, as reported by project geologists. Addressing the varied geology required an adaptive approach to tunnel construction. Where solid rock allowed, the TBMs used open mode, lining the tunnel with precast concrete segments. In unstable zones, however, engineers employed the sandwich method. First, shotcrete was applied directly to the rock face, followed by a waterproof membrane, and finally, a reinforced concrete inner lining. This flexible, multi-layered approach provided immediate support in weak areas and ensured long-term stability against both rock pressure and water ingress, according to technical papers by Alp Transit Gotthard. Our next megaproject spans the Pearl River Delta, connecting Hong Kong, Zhuhai, and Macau. The Hong Kong-Zhuhai-Macau Bridge, HCMB, completed in 2018, is a 55-kilometer bridge tunnel system, the world's longest sea-crossing structure. Its ambition was to drastically cut travel times and integrate the region. The China Communications Construction Company, CCCC, spearheaded this colossal undertaking, facing unique structural challenges presented by deep, typhoon-prone waters, a busy shipping lane, and a delicate marine ecosystem. Building a structure of this magnitude in the South China Sea brought engineers face-to-face with nature's raw power. The region is highly susceptible to typhoons, with sustained winds capable of generating massive waves and imposing extreme dynamic loads on structures. Furthermore, the area is seismically active, requiring the bridge and tunnel to withstand significant earthquake forces. Reports from the project's engineering team underscored the need for designs that could endure a century-level storm and a magnitude 8 earthquake, a truly formidable structural specification. To meet these extreme demands, engineers adopted extensive modular prefabrication and precision installation techniques. Entire bridge sections, including deck units and piers, were manufactured off-site under controlled conditions, then transported and lifted into place by specialized heavy lift vessels. This method not only improved quality and speed but also minimized construction time in the harsh marine environment, reducing exposure to adverse weather and enhancing structural integrity. According to CCCC, over 90% of the bridge components were prefabricated. A crucial segment of the HCMB is its 6.7-kilometer immersed tunnel, designed to allow large cargo ships to pass above without obstruction. Constructing this tunnel presented distinct challenges, achieving perfect alignment of massive tunnel segments on the seabed, ensuring watertight seals under immense water pressure, and managing the dynamic forces of currents and tides during installation. Furthermore, the construction had to minimize environmental impact on the sensitive marine ecosystem, including the rare Chinese white dolphin, a concern highlighted by environmental reports. The immersed tunnel was built using 33 massive prefabricated concrete segments, each weighing up to 80,000 tons. These segments were fabricated in a dry dock, floated to site, and then precisely lowered into a dredged trench on the seabed. 2 artificial islands were specifically constructed at either end of the tunnel to transition from bridge to tunnel. The most critical aspect was the underwater joining of these segments, relying on advanced GPS positioning and precise ballast control to achieve millimeter-level accuracy, as detailed by the engineering teams. Our final destination is 400 kilometers above Earth, the International Space Station, ISS. A collaborative effort by 5 space agencies, the ISS is humanity's most complex engineering project, continuously orbiting since 1998. It is not just a structure, but a permanent research laboratory in the unforgiving vacuum of space. As noted by NASA, its assembly and continued operation present challenges that transcend terrestrial engineering, demanding solutions for microgravity construction, extreme temperature fluctuations, and continuous life support far from home. Building the ISS wasn't like any construction project on Earth. Each module, weighing many tons, had to be transported into orbit and assembled in microgravity. This meant that traditional construction methods, welding, bolting, lifting, were entirely rethought. Astronauts, often assisted by robotic arms, had to perform delicate and dangerous extravehicular activities, EVAs, or spacewalks, to connect modules and install vital components. Sources from ESA and NASA detail the immense training and precision required for tasks where a dropped tool could float away forever. The solution relied heavily on advanced robotics and ingenious docking mechanisms. Key components, such as the Canadian-built Canadarm2 robotic arm, played a pivotal role in grappling and precisely maneuvering massive modules into position. Automated docking systems allowed uncrewed spacecraft to deliver new sections and supplies. This combination of human spacewalks and robotic precision enabled the modular, step-by-step construction of the station, transforming individual components into a cohesive, structurally sound orbiting complex, as described by Canadian Space Agency documents. Once assembled, the ISS faces the relentless hostility of the space environment. It endures extreme temperature fluctuations, swinging from -150 degrees Celsius in shadow to +120 degrees Celsius in direct sunlight every 90 minutes. Beyond temperature, the station is constantly bombarded by micrometeoroids and space debris, and exposed to harmful solar and cosmic radiation. Protecting both the structural integrity of the modules and the lives of the astronauts from these multifaceted threats is a continuous and complex engineering challenge, according to JAXA's mission overviews. To ensure survival, the ISS employs sophisticated thermal control systems, including ammonia-filled radiators that dissipate heat and multi-layer insulation that reflects sunlight. For protection against impacts, critical modules are often equipped with Whipple shields, multiple thin layers designed to vaporize incoming debris before it can penetrate the main hull. Radiation shielding, while limited by weight, is incorporated into module design and operational procedures, protecting the crew. These engineering marvels collectively transform a hostile void into a habitable and functional outpost, a testament to international collaboration, as stated by Roscosmos. From the towering heights of the Burj Khalifa to the crushing depths beneath the Alps, across vast typhoon-prone seas, and into the silent vacuum of space, these megaprojects stand as monuments to human ingenuity. They represent moments where engineers didn't just build bigger, but fundamentally rethought how we interact with and overcome our environment. The structural challenges were immense, often bordering on the impossible, yet through innovation in design, materials, and construction techniques, these visions were realized. They are more than structures, they are powerful narratives of persistence, collaboration, and humanity's unyielding drive to redefine what is possible.